My name is Skylar McCaw, and welcome to my Lab 3 video, all about finding the mass of a black hole. For this lab, we were given some information about a star black hole system and told to create a program to utilize this information to find the mass of the black hole. The information we were given was the mass of the star, position data for the star, delta T, and the position for the black hole, which was the origin of the system. The position data was unique to my experiment and created using this seed. For the code portion, we were given a starter code we had to alter to run properly for this experiment. In order to do this, we needed to implement concepts from Newton's second law, aka the momentum principle, as well as Newton's law of universal gravitation. The equations from said concepts are listed above. Here's the code I used to create the model. I started with the version given and altered it to fit the experiment needs. The first thing I did was put in the mass of the star, 2.0 e to the 30th, and delta T, 86,400 seconds. Next, I put in the equation for the initial and final momentum. P initial is the mass of the star times the initial velocity, and P final is the mass of the star times the final velocity. Next, I found the equation for change in velocity, V final minus V initial, and the change in momentum, P final minus P initial. Knowing these, I was able to find change in momentum over change in time, which is delta P over delta T, which is also equal to F net, according to the momentum principle. Now that we know F net, we need to separate it into its parallel and perpendicular components. Let's start with the parallel component. To calculate this, we first need to find the unit vector p hat and the derivative of the magnitude of the momentum with respect to time. P hat works out to be P initial divided by the magnitude of P initial, and d mag P over delta T is equal to the magnitude of P final minus the magnitude of P initial over delta T. These are multiplied to get dp dt parallel, which is equal to F net parallel. Now, for F net perpendicular, we are going to use a different method to get this value. Since we already know the value of dp dt and dp dt parallel, we know the dp dt parallel plus dp dt perpendicular equals dp dt. We can just subtract dp dt parallel from dp dt to get dp dt perpendicular. And lastly, we just set F net perpendicular equal to dp dt perpendicular. What is the source of F net? Looking at the data, gravity seems to be the only force acting, so we can use the universal law of gravitation and set it equal to F net. This can be used to get the mass of the black hole by moving the equation around to solve for one of the masses. Now here is the last of the code, solving for the mass of the black hole. MBH is the mass of the black hole and is set to the altered version of the universal law of gravitation. I've also included a count meter as well as summed up all the masses, so I can divide that number by the number of entries to get an average for my data. In this lab, F net and the change in momentum are mathematically equal to each other. We calculate the parallel and perpendicular components of the change of momentum and then just set them directly equal to the corresponding F nets. They are, however, conceptually different. Net force is external and acts upon the object, while momentum is internal and is the motion within the object, and forces cause change in momentum. What if the current black hole we just solved for the mass of was swapped out for a different new black hole with a different mass? Would we be able to tell? The answer here is no, unless we were given new data that corresponded to this new black hole. The data we were given from the previous black hole, the position versus time, was used in the universal law of gravitation to find the mass of that specific black hole. So if the mass of the black hole changed after the data was collected, we would have no way of knowing. Thanks for watching.